Laboratory Manager for First Battery, Tracy Kotze. She's here today to enlighten us about battery technology and what we should know about these everyday products that our lives have literally come to depend on. Tracy, over to you.
Thank you, Kathy. Good afternoon, and thank you, everybody, for this opportunity to tell you more about batteries. These days, it's less likely that you'll hear somebody boasting about the size of their SUV or the size of their holiday home in Plet, and more likely that they'll be boasting about the size of their home inverter and battery bank. So I'm here to tell you a bit more about batteries. I work for a company called First Battery. We manufacture and trade in total energy solutions. This first slide shows you a bit about our brief history. I'm not going to go into all the details and bore you with all the different steps, but just want to point out that we've been around since 1931, so very close to 100 years now. Our main retail outlet is the First Battery Center franchise. There are about 126 First Battery centers within South Africa, so there's definitely one close to you. If you're looking for one and you can't find the nearest, we also have a toll-free number that you can phone in order to find your closest battery center. So today I want to talk about specifically SLR batteries. The topic of batteries is massive and much too wide a scope to cover in a presentation like this. So I'm specifically focusing on an SLR type application today. What does SLR stand for? A few people have asked me that today already. Starting, lighting, and ignition. So an SLR battery is the type of battery that would be in your vehicle or your car if you have an internal combustion engine. So if you have a vehicle that runs on petrol, you will have an SLR battery in your car. So there's some examples of our range of SLR batteries. So the first thing I want to talk about is lead acid versus lithium ion. Lithium ion has become a very hot topic also in the last few years. So what's the difference and how do they weigh up against each other? So I'm going to look at a couple of different categories here, starting with energy density. What is energy density? Energy density is the amount of energy the battery can supply in relation to the weight of the battery. Lead has a distinct disadvantage here in that it's very heavy. Lead as a metal is very heavy. So a lead acid battery tends to have a much lower energy density than the lithium ion. Lithium ion definitely has an advantage in this area. The second category is cycle life. What is cycle life? Every time you discharge and recharge a battery, that would be classified as a cycle. So the number of cycles that battery can supply before it dies. Okay, so cycle life, lead acid has a disadvantage, slightly fewer cycles than a lithium ion can supply. Weight, again, I spoke about weight earlier. Lead acid tends to be on the heavier side. This may or may not be a disadvantage depending on the application. If you are putting the battery into an application where it has to move, for example, an electric vehicle, it's going to be very difficult to build an electric vehicle that can run off lead acid batteries because of the sheer weight of the batteries. However, lithium ion works well in that environment. Excuse me. So the next category is temperature range. So lead acid, again, can operate in a very wide range of temperatures, from minus 30 degrees Celsius, which is pretty chilly, up to about 80, 90 degrees Celsius, so pretty warm. Lead acid can work across that entire range. However, lithium, not so keen on the extremes of temperature. The safety, lead acid has a very good safety record. Lithium ion is classified as an average safety record. A lot has been done in the last few years to make lithium ion safer, and I'm sure development will continue in that area to make the technology ultimately a lot safer. So I think we'll definitely see that in the future. But in the meantime, it's always fun to watch YouTube videos of Teslas burning. The next category is recyclability. And here lead acid has a very strong positive, very high recyclability. And especially as first battery, we feel very responsible for the recycling of lead acid batteries. Lead is not a very friendly environmental element, and we don't want it to get out into our water, our air, our soil. So it's very important that we are responsible when it comes to recycling, and we generally take a battery back for every one that we sell. This is very important to us in order to not get lead into the environment. You even get a rebate if you bring back your used battery when you buy a new one. So lithium ion at this stage doesn't have a commercially viable recycling stream. So I think that's definitely a project for students to consider in the future. I think if you can find a way to, a commercially viable way to recycle lithium, I think you will definitely have your future made. Price, here again, lead acid has the advantage. Lithium ion still very high prices for the average consumer. And this is why, generally, when looking at this whole table of comparisons for an SLR application and also for many other applications, lead acid still has the advantage because of the higher price of lithium. As more lithium batteries are made, more factories are making, the price is going to come down. All right, so how does an SLR battery work? So SLR battery is essentially a box of chemicals, converts the chemical energy into electrical energy. What you need to make it work, you need a positive electrode, a negative electrode, and you need some sort of electrolyte, which is generally a liquid, can also be a gel or a paste. So I want to tell you just very briefly today how an SLR battery is made. So these are the main processes: oxide production, grid casting, pasting, curing and drying. Sorry, I went a bit fast there. Curing and drying, assembly and formation. So starting with oxide production. So the first step in our process would be to take the solid ingots of lead. You can see them on the left-hand side there. We melt them down and we cast them into little barrel-shaped slugs that look something like this. These then go into a ball mill. And a ball mill is essentially just a big rotating drum. So what happens in the drum, the slugs rub against each other, they oxidize, and we form lead oxide, which is this sort of grayish-orange powder. We then use that. Okay, that's just the ball mill system again. Okay, so that's the first step. Sorry, I'm jumping ahead of myself here. So that's your first step, is to make the lead oxide. So this is the basis, it's going to be the basis of your active material or the paste in your battery plates. The second part, so this is going to ultimately be your, if you think of this as being the flesh of your battery plate, the next part is to make the skeleton, which is grid casting. So the grid is your basic structural element. So these are what some of the grids look like. It's very important that they have high mechanical strength and also be very conductive, because this is the current carrying part of your battery plate. We use two different techniques to make the grids. The first one, okay, is maybe not so clear on these pictures, but it's a mold cast. I think most of you would be familiar with a mold casting, where you have the imprint of the grid on the one side of your mold, on both sides of your mold. The mold closes up, the molten lead flows in the top, hence the gravity casting fills the mold. As you open the mold, your completed grid will drop out. As I say, looking something like that. There you can see the positive grid in the presentation. Another procedure that we use is called concast or continuous casting. Here you have a wheel, and the imprint of the grid is on the wheel. You have a shoe that fits over the wheel, and the molten lead is fed in between the two. As the wheel pulls away from the shoe, your grid comes off in a long, thin, continuous strip, and you can see that again on the right-hand side of the presentation. There we go, that's your negative grid. So the next step now is to take your oxide, or the start of your flesh of your plate essentially. We mix that with water and sulfuric acid in a big mixer. Ends up looking like quite a stiffish cement, and then this gets pasted onto your grids. So there you can see the pasting process. starting from your negative grid, going to your finished pasted plate. You can see it's still very thin. You have a thin layer of your paste on covering the grid. The same for your positive grid. The paste covers the grid. Where are we? The last step in making the plates is to go through a curing and drying process, and that helps to strengthen the plates and make them ready for assembly. So during assembly, we first start by in the battery, for the battery to work, your plates need to be electrically separated. So we wrap a plastic separator around the positive plate. That's called enveloping. We then form stacks of alternating negative and positive plates until we form the size of the element that we want to make, of the battery, for the battery we want to make. Now, if you look at the presentation, you can see the next process is to mold a piece of lead across the top of the set of plates, and you join all the negative lugs together and all the positive lugs together, hence to make your cell. We then insert each cell into the battery container. This is your battery container. Sorry, I've got some parts inside. This is your battery container. You can see the space for the 6 cells. We're making a 12-volt system, so it's 6 2-volt cells connected in series. The last step in the assembly is to weld the cells together. So you can't really see so well here, but there's a space between the walls which allows you to weld the different cells together. We use a high voltage welding system, and that completes your electrical circuit through the battery. The last step here is then to add your lid. So this is the lid, fits on top, and that is heat sealed in place to make sure that it doesn't leak. Obviously, this is later going to be filled with sulfuric acid. You don't want that leaking into your vehicle. Got a handy handle when you want to put it in and out, and you'll see here the start of your post, your negative and your positive post. And in the next slide again, you'll see how that is completed. So you'll have an internal post coming from your cells that you've built, protruding into the ferrule on top here, and then we weld the two together to have your completed post. So then we go through a few quality checks, slaughter tester, checks for electrical shorts, pressure tester, and we code the battery. The very last step, I keep on saying the last step, but this is the very last step, is called formation. So at that stage, you'll have your fully assembled battery. You'll have all the elements, all the plates, everything you need for the battery to work, but it'll still be electrically inactive. So your final step is to fill it with acid and to give it its first charge. Now in the industry, we call this formation. You can see a picture there again on the presentation of the formation. We use water baths to control the temperature because I think, as most of you know, if you charge a battery, it tends to get warm. So we use water baths to control the temperature. And then we fit, these are little vent caps, and they fit into the vent holes to close up the battery. And there you've made a battery, 12-volt SLR battery that can operate your car, start your car, and hopefully give you lots of trouble-free winter mornings for the next 4 years. So thank you very much. And Kathy, do you have any questions?
Thanks for that, Tracy. Of course, I have some questions. First, I need to know, can I take this home so that I can weld and put together my own battery?
You could, but you need a few more plates.
It sounds to me that it's a lot. Is it a bit more complex than how you've just explained it? Because you made it seem very simple.
It is a little more complex, yes. But I just wanted you guys to understand the concepts.
Yeah, definitely good to see what actually is inside the battery. Not very often that at least laymen like myself who don't deal with this on a day-to-day basis get to see. I've got some questions for you, Tracy, that have been posted in the Q&A tab, and I'm going to begin with this one. It's from Angelina. Angelina, I say you've been very interactive today, asking lots of questions, but I don't know why that scoreboard is not doing you justice. So maybe you also need to be interacting elsewhere on the platform. But I really appreciate the questions too. So don't get me wrong, Angelina. Angelina wants to know, what's the duration or battery life of the lithium battery?
A lithium battery. It's going to very much depend on the application and the number of cycles, and also your depth of discharge. So if you assume you've got 100% energy in your battery, your depth of discharge will be how much you take out in each cycle. So if you take out 50% or if you take out 80%, it's going to affect the ultimate life of the battery. So there's a lot of factors. Even something like temperature is going to play a part. The higher your temperature, the shorter your battery life. The deeper your depth of discharge, the shorter your battery life. So there's no simple answer. There's a lot of different factors that can affect the life of the battery.
All right.
But lithium, sorry.
Sure. Go ahead.
I was going to say lithium tends to have, quite a significantly higher life than lead acid.
All right. Let's take a look at this question from Homozo, who says, "Hi, Kathy. I teach electrical tech. Therefore, there's a topic on batteries in the curriculum. May I ask if you have battery models to use as teaching modes for demonstration of different types of batteries?" So basically, Homozo probably wants some of this in the classroom.
Yes. There is unfortunately a risk, and you'll see why I've actually have these encased in plastic, is because it is lead oxide that's on these plates. So there is always a risk in giving something like this to students, because we wouldn't want them to endanger their health in any way. So it is a bit tricky to give these sort of models out to students. But I think my contact details, I'm sure, will be available. Maybe he could get hold of me and I could see what I could supply to him.
All right, fantastic. So, Homojo, please try and get those details. We'll also ask the conference team to put up Tracy's contact details in that Q&A session, perhaps just as an answer to you, and you can get in touch with Tracy to see what plans she can make. Cynthia wants to know, Cynthia wants to know, can I use an ordinary car battery for solar?
It's not recommended. Cynthia, eh?
Yes.
Sorry, Cynthia, not recommended. What I've described to you is the assembly of a car battery. If you're building a battery for a solar type application, the design is slightly different. The principles are the same, but you'll have different separator types, you'll have different plate types. Your plates will generally be thicker, you'll have a thicker separator. There are different modifications in order to facilitate the kind of deep discharges that you'll go through with solar. And also the rapid, sometimes very rapid recharges that are required for solar. So yes, it'll work, but it's not recommended. And if you get the right battery, it'll work a lot longer.
So if you're using an inverter system, then how long is the lifespan of that battery?
Again, a difficult one,
Yeah.
Kathy, sorry,
Yeah.
because it depends on things like the depth of discharge, depends on how often it's charged, how often it's discharged, things like how fast you're charging it. It's unfortunately quite complex.
All right.
There's no simple answer, because there's, even as I said, temperature can play a part in how long the battery lasts.
So Cynthia, unfortunately, when the battery does run out that supplies your home with backup power, you can't just take out your car battery and plug it in. That's the bad news today.
It's not recommended.
It's definitely not recommended. And somebody else wanted to know, how many panels do you need for a V2 cell?
Sorry, I'm not the solar expert. They should have asked Matthew.
Okay, no
Yes,
problem. I think
not my field.
that was a question from Henry. Henry, we'll try and get you an answer to your question. We've got a number of experts that, of course, are part of this conference, and they're all keeping a close eye on what's happening in as far as the Q&A tabs are concerned. Tracy, it's been such a pleasure. Thank you so much for your presentation today.
Thank you, Kathy.
All right.